Hi everybody, we are starting our new unit. It's our last new unit of the year on simple harmonic motion. You can expect to have a quiz in about a week. So that would be about the 31st of March. Expect a quiz on simple harmonic motion if you're a Wednesday class. Tuesday, Thursday will probably be April 1st. Not an April Fool's joke. So what I want to do is take you to some notes that I have structured on a packet that I'm posting in Google Classroom. So you can take a look there and find simple harmonic motion notes, or you can take these notes, of course, on notebook paper. Remember, if you don't like my speed, you can make me go faster or replay any points that you've missed. So first question, what is simple harmonic motion? Motion in an oscillating system. So to oscillate means to go back and forth, which on a small scale is vibration. And on a bigger scale is something like a swing on a swing set or a pendulum. So motion in an oscillating system. Can you spell oscillate? Motion in an oscillating system, but more than that, has a couple of really important requirements in which a net force restores the object. A net force restores. So you'll hear talk of a restoring force in this unit. Restores the object toward its original equilibrium position. Toward its equilibrium position. So think about that. You pull on the seat of a swing set, pull it off to the side, you let it go, a force appears which tends to drive it back towards its equilibrium position, but there's more than that. With a force magnitude, that is proportional to the displacement. Let's say directly proportional. It's a linear relationship. Directly proportional to the displacement. Okay, directly proportional to the displacement. And by the way, I hope the SAT went okay for you if you took it. All right, so what we have here is a picture of a single spring and a single mass at 4 different times. Let me see if I have a spring handy. Here's one. So if I have a spring and this is its resting position, I'll move it to the side a little bit so you can see my hand move. I can grab it and I can pull it to the right, in which case it's been stretched. And if I let it go, there's a force that's going to tend to bring it back to where it was before, but it's going to overshoot that and it's going to compress and go past the equilibrium position. Once it's compressed, there's a force that's going to tend to squish it back out again, and it'll shoot past its equilibrium position again, and it will oscillate, go back and forth, in other words, just like this. Now, we're going to spend significant brain power of yours on this unit. So why do we care so much about springs? And the answer is it's not just springs. Granted, they're useful. We use them in all kinds of things, including your cars, shock absorbing system, for instance. But this is a model for a lot of other things, including, for instance, how a jet engine might cause a jet airplane to vibrate. Swing sets and pendulums are actually fun toys and useful devices because sometimes they're used to drive clocks. For instance, you may have seen a pendulum in like an antique grandfather clock. They have other uses. But quartz crystals vibrate, right? Molecules vibrate, subatomic particles. So it is a pretty important field in physics. And we're going to work on a spring and a mass as a model that you can build on then in the future. So the first one's been done for us, as it says, fill in. So we have some things filled in, but there's a really important question here: what formulas apply? Some of these you know already. Remember Hooke's law? Remember your AP equation sheet? You have a look on here, you can find some things about springs that we studied in the fall semester. Hooke's law is the idea that if you pull or push on a spring, the spring pull or pushes back, and it's proportional to how much displacement you have on the spring. Let me zoom in a little bit so it's easier to see. So if I pull with a positive force, the spring exerts a negative force. So for that reason, there's typically a negative sign for Hooke's law. So if we rearrange that, we get a formula for lowercase k. Make sure that has a tall backbone so you can tell it's lowercase. And lowercase k is called the spring constant, and it's the ratio of the force to the amount of stretch that you get. You apply that much force, you get that much stretch. So if it's a really, really stiff spring, it's going to take a lot of force to get a little bit of stretch. Okay, next we have, do you remember this? Non-gravitational potential energy, but spring potential energy. There could be a lowercase e there sometimes because it's also called elastic potential energy. And that is 1/2 kx squared, again, little lowercase a, 1/2 kx squared. Sometimes I put the delta, sometimes I don't. It's okay. And that's the spring potential energy. So when you stretch a spring or compress it, it has stored energy within it. And it's determined by how far you stretched it. That really, really matters, or compressed it, and the spring constant. But then we also have a capital K in this unit. So this is one of those units, again, where handwriting really matters. This means the spring constant. This means kinetic energy. As a spring releases from a compression and goes pushing and makes the mass move, you may have a kinetic energy, in which case you'd be looking at 1/2 mv squared. Don't forget the importance of Newton's second law. Always, always net force divided by mass. And if we combine that with Hooke's law, you can write an equation that says the acceleration will be negative kx, or k delta x, running out of room, so I'll definitely leave off the delta here, divided by the mass. So that was pretty fast. So let's look at that again. Hooke's law, the force of a spring is proportional to the stretch. Here, the spring constant, little k, is that ratio of force to stretch. And anytime I say stretch, it could also be compression. Okay, you ever had a pogo stick? It's a good example of a compression spring. Spring potential energy is 1/2 times the spring constant times the stretch squared. There's our old friend for kinetic energy, because when these things release their potential energy, it turns into energy of motion. Newton's second law can be rewritten with Hooke's law as the force. And this is a really useful problem solver. This one pops up a lot. So we have these 4 drawings here. And what they represent is a spring whose equilibrium position is right there in the middle. And so to start this process at time 0, I pretend that I grabbed the mass when it was over here and I pulled it over there, and I've stretched it as far out as possible. When it's stretched, it's got a displacement x. So that also has another name. That maximum displacement is called A for amplitude. So I'm going to go maybe over here and write capital A equals amplitude. Make it a nice tall capital and you'll remember that. That's how big, that's its maximum, okay? So another way to describe that is x max, the maximum x position that it has. And it also could have a negative side to that that would have the same absolute value. So that's its amplitude A. It's been stretched that far. Now, when it's stretched that far, I pulled it over and I'm stopped a minute. I haven't let it go yet. The velocity at that moment is 0. The force is at a maximum. And notice that the force is going to be in the negative direction because I pulled it to the right. The spring is pulling back to the left. So that's why we're saying the force is directed that way, which of course is going to cause a negative acceleration. The farthest stretch, by Hooke's law, is going to give you the farthest force, the biggest force, right? Biggest stretch, biggest force. And that, by Newton's second law, is also going to give you the biggest acceleration. So now we let it go. What happens? Well, the spring has this restoring force and it shoots back to its equilibrium position. But because of conservation of energy, conservation of momentum, it doesn't stop on a dime there. It's got all that energy, right? You invested energy pulling it over there. So now it's got excess energy. So it shoots through the middle position. Now, when it shoots through the middle position, the force on it is 0, which means the acceleration is 0. And the stretch is 0, right? So if you look right up here at potential energy, the stretch is 0, so x is 0, so it has 0 potential energy. In other words, all of its energy is in the form of 1/2 mv squared. That's its fastest speed. So I'm going to write Vmax. That is its maximum velocity when it zooms through the equilibrium position. So if you want to turn your paper sideways again, you might want to write equilibrium on that line so you know that's the resting position of the spring. You could also write resting there if you like that. All right, so it overshoots. As it overshoots, it has lots of excess energy, I guess you could say. And so it starts pushing into the spring and compressing the spring until it comes to a stop on the other side. So right there, it's gone as far as it can in the negative direction, so its velocity is 0. But it's as compressed as it could possibly be. So this is when the force is at a maximum. Now, is that a positive maximum force or negative maximum force? The answer is it's positive. Remember, the spring is pushing this way, okay? It's been swished. it's got a delta X that's negative. So it's pushing in the right-hand direction. So therefore, it's going to have a positive force. And by Newton's second law, if that's the maximum force, that's also going to be the maximum acceleration, positive acceleration that we're going to see. Now it zooms back towards the middle, and here I've changed our pattern a little bit. Here I want you to look with me at, that's not a V, that's potential energy. Because my question for you is, when it's halfway back, does it have half of its potential energy? So let's think about that a minute. Before we do, maybe we should fill out the other parts. What's the force like there? Well, we're going to use Hooke's law. Force is magnitude, at least, of kx. So right here, the force is going to be k times x over 2 because it's halfway back. And we already said heading that direction, it's positive. Okay, so the acceleration is going to be force divided by mass. So that's kx over 2 divided by m. So the 2 and the m are both downstairs. Okay, so this is giving us a little bit of a hint maybe about what's happening here with potential energy. Let's go underneath and work potential energy for a minute. Spring potential energy generically is 1/2 little k x squared. So that means at this position, we are at x over 2. So this particular x is x over 2. Let me introduce a little color there. You might want to do that also at home so you can see the change and compare it to what you had before. So in other words, I now have 1/2 k x squared and a 1/4 that was not there before. Now I don't want to combine the 1/2 and the 1/4 because I want to look at it and see the difference. This is what I had originally. This is what I have now. So at halfway back, I'm at 1/4 of the potential energy that I had before. So in other words, it is not linear, right? So look at that equation, x squared. This is not going to be linear. So that is 1/4. I guess I'll stick with green here. So that is 1/4 of, try this on. What would I be writing if I wrote 1/2 ka squared? 1/4 of the maximum potential energy that it could have, right? Because 1/2 kx squared for x max, all right? So it's not, when it's halfway back, it is not at half of the energy, okay? All right, well, that is worth studying. So that's one of the things you probably will be asked about on tests in this area. You know, what's the situation for force, acceleration, velocity, and maybe potential energy at those locations? Speaking of potential energy, we have a graph down here. It says for a mass spring oscillator, which by the way, this is what this is called, okay? Label the potential energy and kinetic energy graphs. There you go. The graph is not marked. Is the dashed line kinetic energy or potential energy? Is the solid line kinetic energy or potential energy? Take a minute and decide right now, please. Okay, what am I seeing here? At maximum displacement for the solid curve, I have 0 energy. What happens at maximum displacement? It's pulled all the way out, and before I let it go, it stops. Once I let it go, it goes to maximum displacement on the other end and stops. And then it comes back and goes this way, and I'm not touching it this time, but it goes and overshoots as far as it can, and it stops again. So every time it's at maximum displacement and it's stopped, it would have 0 kinetic energy, wouldn't it? So the solid line here is the kinetic energy. When does it have its minimum potential energy? When it's not stretched or compressed at all. And that's when it's shooting through the middle position. Its resting or equilibrium position is right there in the middle. So that must mean that this dashed or dotted line right here is its spring potential energy. Spring potential energy is the dashed or dotted line. Okay? So how does total energy change? Well, let's see, add these two things together. What are you getting? It doesn't change, does it? It does not. Conservation of energy, right? There's no external work done on the system. No outside forces acting on it. So that does not change. Now, where's it moving the fastest? When it zooms through the equilibrium position. When x is equal to 0, potential energy is 0, right? Let's link those two together right there. So if all the energy is potential, all the energy that was potential when I stretched or compressed it is gone, then therefore it's got to have still the same amount of energy, but it's all going to have to be in the other form, okay? All kinetic energy. So where's kinetic energy 0? Where it stops. It stops at -A and +A. Capital A means amplitude, okay? That's the same as negative X max for maximum and positive X max. Those are the two locations at which it stops, okay? Where's the acceleration 0? Let's see, acceleration comes from force, right? So wherever the force is 0. So where's that 0? That's at the resting position, at X equals 0. I don't know if we've written that, the equilibrium position here, but you might just want to write that out, the equilibrium position. And sometimes it's called the resting position, not because it stops and takes a rest there, but because it was at rest before you began the oscillation, before some force showed up and displaced it. The equilibrium or resting position is X equals 0. So where's A at a maximum? That's A for acceleration. And the answer is wherever force is at a maximum. Where's that? At the most compressed and the most stretched. Okay, so once again, that's the same as X max positive and X max negative. Just reverse the order there. Where's the velocity 0? Once again, at the ends, at negative A and positive A, also known as negative X max, and you're hearing me say this a lot, aren't you? Positive X maximum. Where's the velocity at the maximum? Well, when none of the energy is in the form of spring potential energy, it's at the resting position. It's zooming through at its fastest speed as it zooms through the middle. Okay, that was a lot. Now, it's not a bad idea at all if you want to take a break here, okay? But that's what's going on. That's what you need to review. That's what's on your quiz next week. Whew. All right, let's continue. The notes packet does, after all. Okay, double the stretch on a spring, like in the previous drawing, and what would happen to the energy? What would happen to the velocity? What would happen to the acceleration at the maximums? Okay, so here's the deal. When you look at energy, we want to remember that energy comes in two forms. I should zoom in a little bit here. So we have kinetic energy and we have spring potential energy. So sometimes you have to deal with those two forms of energy. Sometimes you don't want to because that makes it harder. So if we just choose to look at it where kinetic energy is 0, for instance, then we would know that the total kinetic energy, energy of all forms, would all be as spring potential energy, would be 1/2 kx squared, okay? So that would be 1/2 kx squared in just sort of a normal situation. All right, does that make sense? So I'm just choosing to put all my eggs in one basket. I'm going to make sure that this is the maximum x, and that way I'll get the maximum, and therefore I'll have the energy total. Okay, so if I double the stretch on the spring, what would happen? Well, let's see, starting with energy. Energy equals 1/2 k, and here I go with a contrasting color again. Now, is this a good one? 1/2 k, and I'm going to double the stretch on the spring. And that, of course, gets squared. So that means energy new is going to equal twice the energy that I had originally, 2 times the original maximum or total energy in the system. Make sense? Okay. What happens then to V? Well, let's see. Now what I want to look at is that 1/2 mv squared turns into 1/2 kx squared, kind of oscillates and goes, oh, I'm sorry, y'all. I just realized I didn't square that. I was thinking one thing and not writing it. That's 4 times, because I have to square that, right? So the new energy is 4 times. Were you awake? Good job catching that for me. I'm going to stick a 4 there just a minute. I'm going to let my whiteout dry. I was already on the next part. I was already on the 1/2 mv squared part. So basically what happened is we've quadrupled the energy. So if I have 1/2 mv squared, now equal to, that's a 4, remember, is invisible 4 times the original amount of energy. How does that rearrange to solve for V? Well, let's see. V squared would be 2 times 4 times the energy original, right? That'd be 8. So I would have 8 times the original energy, and I would divide by the mass, and that would be V squared. So if I take the square root of it, just rearranging so that I have V all by itself, okay, I'm going to have something different than what I had before. Now, what was it before? So V new is that. Originally, the original was the square root of, what does that look like? 2 times the energy, right? Divided by the mass. So you can see this is changed by the square root of 4. Okay, so I have, I'm running out of room for the next part. I'm going to say, so square root of 4 more. In other words, it doubled. Okay, so if I double the stretch on a spring, I quadruple the amount of energy in the system, and I double the maximum speed. Okay, so there's my 4. Looks like that marker doesn't want to sit on whiteout very well. Last part was what happens with acceleration. I don't know if I can squeeze this in, but we'll try. Zoom in a little bit here. So let's see. I want to know A max. So that would be the F max, right, divided by the mass. That's just Newton's second law right there. So what's the F max? Well, let's see. The force is supposed to be kx, but we doubled the stretch. So I have k times 2x as the numerator of my acceleration. And now I'm dividing by the mass. So I think you can see what happens. A max doubles. So A max doubles also. Kind of a squeeze. I think I wish I'd given you more room there. Okay, so there's a good question for a multiple choice format on the AP exam or on our quiz. And you can let the equations guide your thinking, or you can try to memorize some of those as a way to start memorizing some of those equations. Notice all these equations are not conveniently arranged for you on the AP equation sheet. So you're going to want to be able to play with them yourself. Now, one that is on the AP equation sheet is this one, the formula for the period of a mass spring oscillator. So it's really important that when you look at this, you think about that subscript right there, because there's a different formula for the period of a pendulum, which we're also going to be using in this unit. Okay, so they both start off with 2 pi times the square root of, and then it's m over k. So the mass matters and the spring constant matters. That makes sense, right? The stiffness of the spring and how much mass you have. So if I have m over k, the way I remember that is there's actually an Inuit name of muck that was MUK, that was in a physics problem I used to teach a long time ago. So I always tell myself it's 2 pi times the square root of muck. That helps me remember to write the m first and then the k if you have trouble remembering which is on top. Okay, now let's try working with it. Example 2. If the mass on the end of a spring is doubled, what happens to the period? So let's look at this. T new, there's T original right there in front of us, right? So I have 2 pi times the square root of, and I'm going to write muck with a little room in front of it because I need to double that mass. You can see what happens? It's bigger by the square root of 2, isn't it? So T new is equal to the square root of 2 times the original period. So remember that T is period. Its units are seconds. It's an actual time unit. Okay, now keep in mind that we also know frequency because we looked at period once before. So something that's going to come up at some point is just that period and frequency are inverses of each other. So I'm just reminding you of that right now. Frequency is equal to 1 over the period. And if you look at the AP equation sheet, there's some interesting stuff on there about frequency we'll need and get to another time. Okay, graphs. So graphs of simple harmonic motion. I have an x versus time graph. Right here, this is displacement versus time. What does it mean? What does it look like? Let's walk through that one because you can see the next two are blank. So we're going to have to figure out what the first one means in order to draw the others. So this is also an exercise I want you to practice because this is also something I would expect you to have to do on a quiz or test. Interpret or draw graphs of simple harmonic motion. So what do we have here? A is amplitude. So this spring starts off at the maximum positive. So it kind of looks like the one we had in our notes. And then when you let it go, what does it do? It goes shooting through the equilibrium position. Right here is x equals 0, right? It goes shooting through the equilibrium position until it gets to its maximum on the other side. What is that t over 2 doing there? Well, it's reminding you that a period is time for one complete event. So a period for a swing or a pendulum is not just going forward. It's going all the way back also. So the spring, if it starts displaced over here, has to go all the way to the opposite side and come all the way back to where it was before it can begin to repeat itself. So in other words, if it just shoots from one side to the other, that's half of a period. So that's a useful way to tell time. Capital T over 2 is half of a period. So we see it return to its original position one whole period later. Let's see if we can turn that into a velocity versus time graph. So this is velocity. I'll leave units off. And over here, I don't know if you can read that. It says time. Okay, and we have these axes lined up so that they're the same. What's the velocity like when it's pulled all the way to the right? Well, it's not moving. That's where it stops and changes direction. Or maybe that's where I started it from. What's the velocity like? Do the easy parts first, my hint. What's the velocity like when it's gone all the way over to the other side? Well, when it's gone all the way over to the other side, it stops again. It's about to reverse direction again. So I can say, at half the period, it's going to be way at one end and then way at the other end, right? And then eventually it's going to go back to where it was in the first place, and it's going to stop again. So every time it's at a maximum extreme end of its position changes, it's going to stop. Now, where is it at its fastest? Right there when it zooms through x is equal to 0. There's no stretch, no compression, no force, no potential energy. So that means all of the energy must be in the form of kinetic energy. So now think direction, okay? So right here we have a maximum velocity. Is it positive or is it negative? Let's see, we started at positive A, like on the right in our picture on the previous page, and it's zooming into the negative territory. That's a negative velocity. So right there at that x equals 0 position, that is my maximum negative velocity. So my graph is looking like this. Now what happens? It gets back to the resting position, zooming through on the way to the positive maximum. So that's a positive velocity. Right there, okay, it's at its maximum positive velocity. So you can try to draw these as smooth curves. Oh my goodness, is that starting to look like a sine or a cosine? And by the way, don't forget, sine and cosine are the same thing. They only differ by how you move the graph paper behind them. Okay, so I'm going to stop there so you can have some more practice drawing that. And we'll do one more right now. Let's take a look at the acceleration graph. Acceleration versus time. When is acceleration 0? Acceleration depends on force. So that would be whenever force is 0. Okay, so what that means is if it has its maximum acceleration, that would be where the force is at a maximum, wouldn't it? So right there at the far right-hand end of the previous picture, it's stretched as far as it can stretch, and if you let it go, it's going to go shooting to the negative side. It sounds like negative acceleration, doesn't it? And it's at the maximum because that's where the negative force is at a maximum. So I'm going to label this negative a, lowercase a for acceleration. Lowercase a max, negative a max. When is it a maximum again? When it shoots through to the other side. Okay, so that right there is when it's shot through to the other side. So it's at maximum negative position. So our spring is compressed all the way on the left, and now it's going to have all the force and all the potential energy, and it's going to shove it back to the right. So right there, we have our maximum positive acceleration at the other side of the oscillation. So this is going up. Wait, where's acceleration 0? Where force is 0? Where's force 0? When it goes shooting through the equilibrium position. At its fastest speed, it has no more spring compression. So what's going to happen here is your graph is going to do this. And again, I'm going to stop right there and let you work your way through those. Let me just give you one more formula right now. This is the formula for the period of a simple pendulum. Also in the AP equation sheet, I want you to make sure you know it. So this needs to have a subscript. This is the period of a pendulum. What does it depend on? It depends on the length of the string and the planet that you're on. That's G as in 9.8, negative 9.8 without the absolute value, but we want the absolute value here, right? So the square root of the length of the string divided by 9.8 meters per second squared. That square root times 2 pi will give you the period, the time it takes for a simple pendulum to go all the way from one end to the other end and back to the beginning. Okay, so one complete cycle. All right, since we played around with the formula for the period of a spring up here, we need to play around a little bit before we go with the period for a pendulum. If the mass on the end of a pendulum is doubled, what happens to its period? So let equations guide your thinking. Write down the formula again for the period of a pendulum. By the way, memorizing these is really smart. It saves you a ton of time. How do you memorize this one? It's easy to remember. G is on the ground, okay? Gravity comes from underneath, something like that. Look at that formula. Do you see M in there anywhere? The fact that M is not in there tells you that mass does not determine the period of pendulum. So nothing happens to its period. That's our first question, okay? That's our first answer right there. Now, what if the length is cut in half? Okay, well, we could look at that and have that as our original one. And let's say this is period nu. Got my color going again. Period N for nu, or write out the word, either one. And I'm going to write that equation as a very tall stack. I'm going to have a numerator and the denominator is G. Personally, when I have something that's partially a fraction, I like to make everything a fraction. So that's L over 2, that's my new numerator. So let's just make the denominator G over 1. It's a little bit easier maybe to see what happens if you flip it and multiply. So now if I flip it and multiply, or I do what I like to call outsides over insides, L divided by 2G, that 2 is blue, isn't it? So what's the difference? By the way, I forgot to write the 2 pi. I need to do that. So 2 pi times the square root of L over 2G. What is that? Well, that's the square root of 1/2, isn't it? That's the square root of 1/2 times 2 pi times the square root of L over G. Again, we don't want to cancel out the, anything. We want to try to see what we had originally, 2 pi. So we can see now our new one is square root of 1/2 times the original period. Okay, are your brains full yet? They might be, especially if you are doing this on Wednesday and you took the SAT today. So with that in mind, let me just remind you that that's a lot of new material and you need to study, okay? We're gonna be using this in class at what might seem like a really fast start. So this is a great time for index cards, flashcards with Quizlet or Anki, any of those things like that that can really help you. We'll continue this with more sample problems in your notes and more notes and lots of opportunities for you to